Swayam Prabha. Digital India. Educated India.
Introduce our guest speaker, Dr. Shreyas Melkote. Dr. Shreyas N. Melkote received his Bachelor of Technology with honors in Manufacturing Science and Engineering from the Indian Institute of Technology, Kharagpur, in 1987. His MSME from Washington State University in 1989, and his PhD in Mechanical Engineering from Michigan Technological University in 1993. He did his postdoctoral training at the University of Illinois at Urbana-Champaign prior to joining Georgia Tech in 1995. Dr. Shreyas N. Melkote is the Morris M. Bryan Jr. Professor for Advanced Manufacturing Systems at Georgia Tech, where he also serves as Associate Director of the Georgia Tech Manufacturing Institute and Executive Director of the Novelis Innovation Hub. His research focuses on robotic machining, physics-based modeling of manufacturing process, and data-driven cyber manufacturing. Dr. Melkote has published over 250 peer-reviewed papers and received numerous awards, including the ASME Blackwell Machine Tool and Gauge Award and the SME Dell KLN Outstanding Young Manufacturing Engineer Award. We are really happy to have you, sir, eagerly looking forward to your valuable insights.
Good morning. Thank you for that very kind introduction. Wasn't necessary, but I appreciate it. Hope all of you have had a productive morning with Professor Samuel's presentation. He's introduced you to laser micromachining using femtosecond lasers. So we'll continue that theme. I'll talk about using lasers, but not using lasers by themselves for manufacturing, but using them as an assist or as assistive, let's say, source of energy to enable material removal processes, okay? Such as machining and grinding. Those are kind of things. And we'll see how far we get today. We'll do the same thing. I enjoyed the discussion last time, yesterday. So feel free to raise your hand, ask me questions, treat it just like a classroom. And I think it'll make for a more interactive and more hopefully beneficial to your understanding session. So I will stick to micromachining for most part, although some of these ideas that I'm going to talk about are not restricted only to micro scale machining. Okay, that's where we first started, but you can use it for other more conventional scale machining, and that's what people have done. Micro hadn't been done a lot. They hadn't done a lot of work in micro. That's where we started. So this is the agenda for today. Again, like yesterday, we'll see how far we get, depending on the Q&A. I guess I don't have to motivate why there is interest, or there has been interest since the 90s, maybe even predates the 90s, but there's a concerted effort, largely in Japan actually, in the 90s to try and miniaturize. I mean, as you know, they have been at the forefront of miniaturization. But miniaturization is by itself not new. In semiconductor world, people have been doing miniaturization for a long time, right? With silicon material as a substrate for integrated circuits, for example, right? So that's not new by itself. But for electromechanical products, keep in mind, semiconductor manufacturing typically is a 2.5 dimensional process because you're dealing with a substrate and essentially building up in layers different structures, if you will, for that enable you to create a circuit. But and also you have very controlled materials in semiconductor manufacturing. Whereas in the real world, we as mechanical engineers live in a world where our products are three-dimensional. Also, we deal with a wide range of engineering materials, right? All the way from metals, non-metals, all kinds of materials, and most complex products involve multiple materials, not just one, right? And so it's a much more complex problem, and it's less tightly controlled in terms of material properties and so forth. So having said that, in the 90s, a lot of effort to try and miniaturize, make small things, all the way from driven primarily by, medical industry, biomedical devices, for example, implants, to even surgical tools and so forth. Electronics as well to some degree, like printed circuit board drilling is an old idea. Historically, before they switched to doing laser drilling, which is what is done more commonly today to produce vias, or even chemically, they would do through etching processes. It was done through drilling, mechanical drilling, right, to produce those holes, if you will, to generate circuits in different layers of a printed circuit board. So, and aerospace as well to some degree. So these are the drivers, have been the drivers historically. I'd say medical is probably at the forefront, and maybe some other non-defense related applications that might be driving some of these. But biomedical devices, I think, is one industry that I know uses micromachining techniques, whether it's laser micromachining or any of the other types of micromachining techniques, much more extensively than most other industries do. All right, so we'll focus on mechanical micromachining, as I've already motivated. I'm a mechanical engineer. And we are talking about, and Professor Samuel already yesterday showed you, he talked about miniaturization. He showed you a small lathe on a palm of somebody's hand, right? As an example of producing small scale machines. Do we need big machines? And the question you might ask is, besides being a novelty that, hey, I can produce a lathe that sits on the palm of my hand, but what good is it? Is it useful? I mean, just because I can do it doesn't mean it's useful, right? I think a lot of that is driven by the fact that when you're producing small parts or small features in small parts, then think about it. There are many factors that influence accuracy of something you produce. Temperature fluctuations, right? Stiffness, right? Because any kind of a mechanical process, you're using forces, right? A tool is interacting with a workpiece, and there are forces involved. So if you have very small features, they can deflect very easily, which will impact accuracy. So if you're producing something on the order of few hundred microns, then your tolerance on the features you want to produce should be at least one order of magnitude better, right? Well, that drives, somehow you have to control size. Now, clearly, the larger the dimension, as you know, very simple concept from, alpha times delta T being the temperature variation and alpha being the coefficient of thermal expansion. You know very well that even small temperature changes can produce significant change in dimension, especially you're dealing with large dimensions. So if you reduce it, obviously you're going to minimize that effect, right? That's part of the motivation as well. Okay, having said this, there was a big effort since the 90s to try and see, can we use conventional machining or material removal processes like milling, turning, etc., drilling, and so forth, to produce micro and scale them down to be able to produce, as opposed to millimeter scale features or tens of millimeter scale features or even larger features down to on the order of 100 microns, sub-millimeter features, really, right? Nominally sub-millimeter. So typically when people talk about micromachining, they're referring to something that's sub-millimeter, either the feature size or sometimes even the component size itself, okay? So that's the goal. But in reality, some of these challenges apply to objects or parts that are on the order of a few millimeters, okay? Like on the one example I showed you earlier on, which is the fasteners. These fasteners are fasteners that are, you can hold them in your hand. You can see them. They're not that miniature, but they have features in them that are on the order of a millimeter or less, right? And then, so you have to produce in large components, small scale features as well, okay? So those also fall under the umbrella of micromachining. Okay, so we want to be able to create 3D features in a wide range of materials. And why not just use a laser? or some other method, right? Because lasers can machine and there's no contact, there are no force issues or very little, at least if any kind of compliance related errors are going to be minimized substantially. Why not do that? Well, part of the reason is that mechanical removal processes are faster, okay? They're proven, you can generate pretty good surface finishes. You can also, to some degree, control thermal damage in the material, okay? And therefore, laser-based, now of course you do have, as Professor Samuel mentioned, femtosecond lasers or picosecond lasers where you essentially are ablating theoretically under cold conditions, without producing significant thermal damage. That exists, but again, you cannot, they're slow processes generally, okay? The energy densities are much smaller typically. And so they're suitable for certain things, like, we're talking about a heart stent that's actually made using a laser micromachining process. So there are reasons to consider using mechanical machining methods. But what's the challenge? Okay, so now I made the case that there are applications where mechanical micromachining is something that has value. Oops, sorry. So let me get the pointer. Okay, so what are the challenges? Well, if you're going to make small scale features, you need small scale tools. So today you can purchase tools down to 50 micron milling tools, for example, down to 50 microns or even less. People have actually produced 5 micron end mills. It's just for novelty. Nobody uses them. But what you can buy commercially, maybe up to 25 microns in diameter, right? With 1 or 2 flutes or cutting edges on an end mill. You can see one picture here of a typical end mill. Looks like a conventional end mill except scaled down in size on the order of about 40 microns, right? Only a small portion, the tip, is where the cutting flutes are. So you're restricted to making small scale features, right, in this. But what's the challenge? Tool strength is a challenge, right? Now, if you're machining soft materials like polymers or, very soft metals, then it's less of a challenge, right? But if you're machining something difficult, you want to make micro scale features in titanium. The biomedical implants, many of them are made out of titanium, chrome alloys, and other types of compatible materials, right? And therefore, those strong materials. They're strong both in terms of high temperature strength. They also tend, so that makes them difficult to machine or to cut, right? So stiffness can be an issue as well. Obviously, that's one reason why the tip is conical. You see the diameter of the shank is 4 millimeters. It's not that small, but the tip, which is, has a small length and has a diameter of 40 microns, is a very small portion of the overall tool. It's to minimize compliance or lack of stiffness, right? They've already done that, but still it can be, depending on what you're cutting and what forces are involved, that the rest of your machine structure, if it's not rigid enough, can cause problems in terms of deflections, for example. So those are a couple of things. And then where are these tools? They are very small to begin with. And you're trying to produce features on the order of hundreds of microns. And you obviously the tolerance on those features, if there is a tolerance specified, would be 1 order of magnitude smaller. So any small amount of wear, if you're especially trying to make these types of features in difficult to machine materials, any small amount of tool wear can be a problem, right? You will actually deviate from the tolerance, specified tolerance. So most of these tools tend to be made out of a fine grained tungsten carbide, which is the same material that's used for even conventional scale cutting tools. And they may have coatings and so forth. Although coatings for these tools is not that simple to do. Early days when people were making these tools, if you looked at the tool under a microscope, a high magnification microscope like a scanning electron microscope, you'd see that the coatings are very, very non-uniform. Clumps of material as opposed to nice, thin, uniform coating. But that they have improved. These days you can buy them, depending on the manufacturer, decent quality cutting tools, coated tools. Now, what are the approaches to try to overcome these challenges, right? Especially if you're trying to produce these features in difficult to machine materials, right? Like I mentioned, titanium or ceramics for that matter, right? Sintered ceramics. And we'll talk about that as well. And so, approach is to lower the material removal rate. I'm going to reduce the feed speed, depth of cut. That's one way to reduce forces and extend the life of the tool. But obviously that's counter to what you would like to do in practice. You want to produce the feature as quickly as possible, not as slowly as possible, unless you have no choice, right? Lubrication is another way. You can extend the life of the tool by lubricating, minimize, increase energy dissipation and things of that nature, or reduce friction. Tool coatings, obviously we mentioned. One other way would be hybrid processes, okay? All of those first three methods are valid methods, except they may not be economical, okay, for certain applications, which is why we want to come up with other methods like hybrid, such as by trying to alter the state of the material that presents the challenge. Why is strength of the tool a limitation? Obviously, I can make a tool out of cubic boron nitride or diamond, something like that, but that becomes very expensive. They are very hard, and for certain applications, they may work, but they're very expensive. So it's not a practical solution, right? Instead, if I can somehow control the strength of the material that I'm trying to produce these features in, somehow lower the strength in a controlled manner, very locally, then I will reduce the forces involved, or how difficult it will be for me to produce the material, remove the material is reduced. And that's the approach, that's the idea. So one way to do that, as you know, certainly for metals and including for ceramics, what happens to the strength of the material when you heat it? It reduces, right? Strength reduces with temperature. So that's a very basic physics. All of us understand it. And that's the idea, right? Is to take advantage of that basic understanding. But you have to do this in a controlled manner. Yeah, you can't soften the whole thing, because then that'll alter the properties of the component that you're going to be producing. So how can you do this? All right. So the approach is a little different. Softening is one way, right? Thermal softening is one way. It'll work for metals. It'll work for certain non-metals as well. Certain ceramic materials, it'll work as well, okay? Certain ceramic materials will soften at reasonable temperatures. But usually ceramics have a very high softening temperature. The strength they mean, that's why you use them actually as well, right? Therefore, good wear resistance and so forth. So the basic idea is illustrated in this chart, where you see that you have a laser beam. Laser is one way. It's not the only way. You could use some other energy source to generate thermal softening. But lasers have an advantage in the sense that they have very coherent energy source. You can actually tailor the properties of the laser, in particular the wavelength, to match the material, right? And also you can control the size of the heat source by controlling the spot size, okay? And you can control the energy density as well by controlling the spot size, for example. Even with a low power laser, you can reduce the spot size, and that power or energy that is irradiated on the surface over a very small area will give you very high energy densities, right? So those are advantages, right? And laser technology has come a long way. Today, you can actually laser pointers, a lot of you use them, right? And obviously, they are designed to be safe for you to operate, right? There are different classes of lasers that Professor Samuel may have talked about, right? So they belong to a class of lasers where they don't present challenges. But anything we want to use here would be a laser with sufficient energy density that can actually harm us physically, okay? So that's the type of lasers that we are talking about. Power itself may not be very high. For those of you familiar with additive manufacturing, metal additive manufacturing machines, they have on the order of kilowatts, right? They'll have tens of kilowatt, a few kilowatts of laser power, for example. You don't need. Now, the earliest days when people used this idea of actually using lasers you can trace it back into the 80s and 90s when lasers were developed in the 60s. So in the 80s, people were using CO2 lasers, okay? These are gas lasers, basically, CO2. And they're huge. They occupy the size of this room. And that's not practical, right? Unless you're doing it for some very specialized applications where money is no object and that can usually only be for national defense or something like that, where you are willing to spend that kind of money. It is not practical for you to use such systems for, commercial applications. So having said that, laser is what is used here. So laser is pointed at a location some distance away from the tool, mechanical tool. That's the basic idea. So I want to soften the material that the tool is going to see as it moves around and cuts material the way a typical machining process would work, right? So that's the basic idea. You want to control this distance, right? Such that if it's too small, the laser, the heat generated by the interaction between the laser and the material will also affect the tool. And as you know, tool wear is a temperature dependent, the strength of the tool is also temperature dependent. Okay, so if you increase the strength of the tool, this is tungsten carbide, it'll also soften, right? And obviously you won't be able to cut. So that's not required, that's not an idea, that's not good. So you want to control, optimize that distance D, right? Below some critical value such that the material is softened. Okay, so when the tool gets to the point where the laser is, it sees a softer material than the bulk material properties, and therefore it's easier for it to cut, right? That's the basic idea. And this way we can lower the forces generated in the process. And other things we have to look at. What happens to the tool, what happens to the workpiece, etc. Right? Hopefully you can you don't do damage, right? And then only this process works. Otherwise it's not useful. All right, so that's the basic idea for metals. Well, for ceramics, for certain ceramics, you can use the same idea. Certain ceramics, sometimes certain silicon nitride, certain ceramics will actually soften, okay? Sufficiently soften to make it easier to cut. And people have done this. At the conventional scale, people have done laser-assisted turning and so on and so forth, where you actually can soften the ceramic and machine, actually, okay? But this is a different idea, okay? The idea here is I will actually weaken the material. Now, softening is also weakening, except for metals, softening means lowering the yield strength of the material. Whereas the other option for brittle materials, since they don't yield, they don't have, they don't undergo plastic deformation. There are exceptions, obviously. They can under certain conditions, but behave in a ductile manner. But let's ignore that. Just focus on its typical properties. Room temperature, it's very brittle. Right? It's hard, it's high strength, but if you can exceed that strength, you will fracture it. So idea is to induce thermal cracks in a controlled manner. Okay, so you essentially shock the material by exposing it to a laser, okay, again, some distance in front of the tool. And that laser matter interaction, in this case with the ceramic, is going to generate what will heat do? It's going to cause local expansion. Well, ceramics are not very good in tension. They can handle compression, but they're not very good in tension. So the idea is if you apply enough thermal stresses to the material such that you exceed the fracture strength of that material locally, then you will generate cracks and you will weaken the material. Okay, so now when the tool gets there, right, it sees weaker material and it can simply remove it away, remove that region. And you want to control the region of cracking or softening, whichever technique that you plan to use. You want to limit it to the volume of material that's being removed. If it goes outside it, you're damaging other parts of the material, which you don't want to damage, right? So that's the basic idea. Okay, any questions about the basic idea? So ideas are simple. How do you do that and what exactly happens if you do that? Those are things we will talk about, okay? All right. So in order for us to try these ideas out, we need some sort of a test bed for us to do this, right? And we are talking about micro scale features, which means we need to build at that point, IIT Madras has a Kern machine that Professor Samuel mentioned that you will see. Maybe you've already seen, but you will see it if you haven't seen it. And it's a very expensive German machine that looks like a conventional machine, but as he explained, it goes up to 160,000 RPM, he mentioned. So, but that's a very expensive machine. It's a very nice machine, but very expensive, right? For research, we didn't have that kind of money. So we actually built our own machine. Plus the advantage, there wasn't, when we were doing this research, there wasn't a machine that I could buy that would do laser-assisted micro milling, for example. I couldn't. Even a Kern machine doesn't have that. You can maybe buy today attachments, but we are talking about, this is in some mid 2000s time frame when we were doing this, right? So almost 20 years ago, right? So at that time, we said we will build our own. What is the uniqueness of this design? Okay, this machine, you need the laser. Keep in mind, if you're going to do complex features in a milling operation, the tool is going to follow a tool path that's complex. And if you want to soften the material right in front, the laser always has to be in front, right? For it to be softening some material distance D in front of the tool. So we need to design that system. So that's why you have a 4-axis system on the left, right? With a rotary axis up on top. Number 4 is where it's the rotary axis, or number 1 here is the rotary axis, and 4 is the laser assembly, right? And this is a small laser. These lasers back in the day, these are engraving lasers. Today they're used routinely, actually, in industry. They were used back then too, but they're lasers used to engrave. If you look at some, maybe you win an award and your name's carved into the metal. Well, that's done using laser engraving, right? These are relatively low power lasers, somewhere from 5 watts to maybe 30 watts, 35 watts. In our case, we had 2 lasers, and they look like a pencil. They look very much like your laser pointer, except they're very dangerous. You can kill somebody with it, so you shouldn't point it at anybody. So this is the system we design, and you have XYZ stage all stacked. That's pretty standard. And we have a high-speed spindle, okay? This allows me to program 4 axes such that my tool is always, the laser is pointing always some in front of the tool, no matter however my tool is moving. That's the advantage of this design. You see a later version of this. This is the inside of our test bed. And this has some other things put in there for cooling and so forth, right? There's a MQL system there for minimum quantity lubrication, and other cooling and lubrication methodologies also implemented in the system. But that's not as important. We'll talk about it later. So this is a test bed we designed and built for us to do basic investigations. Actually, there's a version of this even earlier where we were doing simply like a planing operation. One of my former PhD students, now a professor at IIT Bombay, his PhD work was the first one where we did this actually, okay? But that's not milling. Milling is more like grooving, only grooving operations. But the ideas were the same. Okay, so here's an example of what we did when we built this machine. You can make, this is in a hardened tool steel. It's a tool and die steel, A2 steel, with about 62 Rockwell C, so very hard. Heat-treated steel, and used for dies and molds and so forth. And you can produce, let's say, spirals like this, or even circles like this, channels, if you will, just to illustrate what you can do. You can produce features like this. You can produce this type of a grid pattern, and you can produce more complex things, obviously, right? In these type of things. And you can see the size of these things. They're on the order of about 250 microns to 400 microns, and even less. You can do 100 micron tools in theory. Of course, you'll have to control the spot size of the laser to ensure that, it's not going outside the region that you want to remove with the mechanical tool, okay? So that's the basic idea. All right. So when we ran experiments using this type of a system, after a lot of work, I'm showing you the final results here, obviously. This is showing you what it does, right? So here you see what this is plotting is the resultant force. You can measure. How many of you, obviously, the researchers here know how to measure forces in a cutting operation, right? I mean, what would you use? Dynamometers. Okay, so there are piezoelectric force dynamometers. They've been around for a long time that are used in the lab. You can only generally use them in a laboratory environment to do research. You won't put them on a production machine, okay? So those tools exist that allow you to measure these things, forces involved in the cutting operation, which is great, and they have very high sensitivity and accuracies as well. So These are this is a mini dyne, the smaller dynamometer that allows you to make these measurements. And here's, some experiments that we did. And basically the idea was to see how does the force acting on the tool change, or on the workpiece, equal and opposite forces act, right, on the tool and workpiece. How do they change as a function of time of cutting? So we were cutting grooves in this A2 tool steel of 62 Rockwell C. The tool is a 180 micron diameter tool. It's uncoated. It's a 2-flute end mill. And these are the conditions. There are 3 conditions. That's why you see experiment 1, 2, and 3. This is without a laser, and -L represents with laser assist. Okay. The laser parameters are shown here. It's 18 watts. The spot size is 280 microns, and D is the diameter. The distance in front of the tool is about 270 microns. These are optimized with some experimentation and modeling. You can model these things, see what the temperature distribution is going to be, because this is like a moving heat source problem. There's a classic problem. There's an entire book written on by Karlsruhe and Jaeger that actually describes how analytical solutions, or some of them you will have to solve numerically, but simply a point heat source moving on a surface, you can actually solve these problems and determine the temperature distribution. This laser has a Gaussian profile. That's also important. The shape of the energy distribution is important. Some lasers have uniform distribution. You can also play with beam shaping today. That's done. But anyway, back then we were not doing any beam shaping. We had optics at the end of the collimator. So this is a near infrared laser. It's a ytterbium doped laser, fiber laser that produces a beam that actually, or photons that actually is nominal wavelength of 1 micron, so 1.06 microns. So it's really a near infrared regime in terms of wavelength, and that works well for metals actually. Okay, femtosecond lasers tend to be obviously different. There are many types of lasers. Professor Samuel has talked about it, so I'm not going to talk about that. But we used 1 micron, nominally 1 micron wavelength beam. Beam size coming out of the collimator is 5 millimeters, and then you use optics to bring it down to 280 microns, right? You can do that. You can play with all of that. So anyway, you could see the point here is to point out the benefit of doing this thermal softening idea, right? So here it's showing you that we milled 8 grooves, right? And with and without the laser, you can see the markers here. So let's look at one just to kind of, let's say we look at the most aggressive case, number 3, right? Experiment 3 is shown here. This is experiment 3. Let me make sure that I look at this correctly. Yeah. So experiment 3 is here. Without the laser is this one here. After 4 grooves, it fractured. Okay. Why? This is the highest feed. The feed is on the order of 13 microns per revolution, which doesn't sound like a lot, but it's a lot for a small tool. Okay. And the depth of cut is 32 microns, the axial depth of cut. Okay. Which is more than number 1, right? The feed and depth of cut are much smaller. So here, without any laser assist, it failed after 4. Now let's look at the corresponding case where we had the laser. Okay. So this is 3-L, which is this one here. And you can see it continues more or less with very little change in the force, right? Over 8 grooves. And we stopped there. We could go further if you wanted to. Okay. Now, this, for the extreme case, it says that with laser assist, I can machine 6 times the material removal rate. If I didn't use the laser, the tool will fail. I can actually increase the material removal rate by 6 times because I can increase the feed, I can increase the depth of cut, the volume material removed can be increased much faster. That's the advantage, okay? One advantage anyway. All right, so the tool breaks. What happens to the shape of the geometry that you're producing, right? In this case, a groove, simple groove. Well, this is without the laser. And what you see here is it shows you it shows you the groove after cutting 5 millimeters only in terms of length of cut. and after 203 millimeters. Okay, so you can see here after cutting 5 millimeters, this is the dashed line, looking at the cross section of the groove, you can see there is, some what you can call as burrs on either side, essentially material being displaced, right? And that's there for both cases. But you can see deviations from the squareness of the groove as you keep cutting, because the tool is wearing. And you will look at the tool wears, and that's what happens. This is without the laser. This is with the laser, okay? And here you can see that, yes, there is some burr formation. It's not zero, but it's less. And even after 203 millimeters of cutting, right, it's there. It's more, obviously, than before. But you can see here the geometry is much more accurate, right? So it's possible for you to not only reduce forces and remove material faster, but also produce a better geometry. It's possible. That's what it suggests, right? Now, I'm making it sound easy. Obviously, in the end, you want some model that tells you what conditions I should use, right? So in the end, but initially, this is what we found. What happens to the material below it? As I said, we want to only irradiate the volume of material, soften only the volume of material that the tool is going to remove. Anything more than that is probably bad, because you're starting with a very hard material, and that's because you want the final product to have high strength, right? Therefore, you want to make sure that after you remove the material, you have not lowered the strength of the material, right? Which would happen if I don't control my energy source or the laser matter interaction properly, okay? Or the amount of energy I'm inputting into the process. So what this shows you is the effect of laser scanning. This is just showing you that, hey, if I were to scan under these conditions, 18 watts, whatever you see here, at some speed of scanning, you can see that there is a microstructural transformation. The material is a steel. It actually gets transformed, right? It produces what appears to be white, generally much harder. It typically is. But if you do it in situ, remember, idea is to heat it and soften it and cut in situ, right? Not wait for it to come to room temperature and then cut. If you do that, it'll be worse, right? Forces will be higher because this is much harder. This white region is much harder. It's phase transformed. It's actually martensitic. Okay, if you all remember your iron carbide phase diagram, right? So with very rapid heating and very rapid cooling, you're going to actually produce martensite, right? After austenitization, and you will actually cause, very hard phase to form. So here you're doing this by controlling it in situ, right? So material the tool sees is softer, but nevertheless, you can see that there is some darker region here. Okay, that's typically how a heat affected zone looks like. It's not too bad. Okay, if you look at welding, in welding, you'll see heat affected zone as well, right? So this is evidence that there is some softening, which is why I'm making the point that you have to control the energy to soften most of the material that you're going to remove to enable easy machining, but not do any damage beyond that, okay? So this is what it says. It's not too bad, but if there is some heat affected zone, in theory, I need to play with my depth of cut, and I need to play with my energy that I'm inputting with the laser, such that it's less than the volume to be removed, and I can do this. That's what, at least conceptually as engineers, we think of, okay, how do I get around it? That's one way to get around it, okay? So it's possible. All right, what happens to the tool? Well, this is showing you the condition of the tool. This is without any laser assist, the top row, before cutting. You see some material, this is before cutting, so you can see that the quality of the tool itself from the manufacturer isn't so great. There are some things sticking to the surface. This is essentially an uncoated tool, but this could be dust as well, okay? That could be dust because it shows up in a scanning electron microscope as being very big. But you can see after cutting for about 101 millimeters, there is some rounding of the corners, right? Of the end of the tool. You see that. There is also, if you zoom in this region, you can see there is some microfracturing that has occurred that has led to removal of material, okay? With laser assist, you see some material adhering, certainly, because now the tool is seeing softer material, so it's going to stick. That built-up edge can be a problem. But you can see that the shape of the tool isn't bad. There is some edge rounding. Now this is cutting twice as long as the previous tool, 200 millimeters, and still it's not too bad, but there is material adhering, okay? That ideally should be removed. It shouldn't happen. You have to somehow get around it, and there are ways to get around it. Without going into further detail, we can talk about it towards the end. That ways to actually be investigated, that through lubrication or other methods, you can actually minimize that, okay? All right. Now that was A2 steel. There are other types of materials, right? Every material will behave a little differently in terms of how it interacts with the laser. This was for a industry project where they were interested in you saw those fasteners, in this case, fasteners made out of A286, which is a high strength steel. It's an alloyed steel with high nickel content. You can see the nickel content is 24.58%. Which is quite high, okay? And nickel, as you know, I mean, Inconel is a super alloy that is used for jet engine turbine blades in the hot section. So, you know, these properties are going to be like that. This is like stainless steel, this particular steel. And so its hardness may not be very high, 42 Rockwell C, but, you know, tensile strength is high. It does oxidize at 700 degrees C. Obviously, if you're adding thermal energy, you can promote oxidation. Oxidation happens much more easily at elevated temperatures and so on and so forth. So we did the study. Now I want to show you a video. So you haven't seen the process. This is actually using just fluid, you know, flooding the zone and micro milling. Okay, a groove. You can see the groove being milled using some oil-based lubricant here, or cool. But this is without any lubricant. This is just with the laser. You see the laser. You can see. You can also see the tool is glowing, okay? But the tool is okay, okay? It can still cut, okay? But obviously you want to keep the tool as cool as possible, but the material as soft as possible or heated as possible, okay? Without melting it. Obviously you don't want to melt. There will be some ablation, but not a whole lot. So that requires some additional methods, but even without that, those results I showed you are using this type of a process like this, okay? So this is on our test bed, this video. So what does it look like in terms of the geometries that are produced? This is looking at, under an optical microscope, dry versus wet. Wet would be that you said submerged case that you saw in the video, versus using the laser assist with 12 watt laser power or 18 watt laser power. You can see here, there are burrs that do form. This dark region that you see here, this black region, are basically burrs. Oops, sorry. These are burrs that form on the side. With lasers, also you still see some burrs that are there. The least burr for the laser-assisted case is for 12 watts, less energy, and therefore less softening, and therefore less plastic flow of material. So this is what happens, increased burr. But burrs can be removed. You can brush it, you can remove it. There are ways to do it. Obviously, you want to minimize it because any subsequent deburring operation is an extra step that would have to be added, right? But we can integrate that even in this process itself. It can be done. Brush deburring can be done. We've done some other work on that. This is looking at the geometry. Now looking at that cross-section, looking at the depth of the groove along the length of the groove, right? And there's a lot of information here. This is for one condition that you see here. And for the 4 cases, dry, wet, and with different laser powers. And what do you see? The nominal depth was 20 microns, 0.02 millimeters. That is what we were trying to do, okay, produce. What do we see? If you use dry, we already saw the cross section, you know, there's deviation there. You can see that we only generate about 15 microns, okay, the depth of the groove, which means that there are different contributing factors to this. One of which I have not talked about, is for these very small tools, you have to determine where the 0 point is before you program. Okay? Does anybody know how a machinist determines where the top surface of the workpiece is relative to the tool? So that would be a more sophisticated way of doing it, where they have a probe, right? They have a probe or a tool presetter where they actually go and measure the tool length, and they know where the part is. So do that. But otherwise, how would they do it? How, they don't have such a presetting tool. Has anybody seen a machinist do this manually? How? So if you, let's say, bring down the tool or raise the workpiece such that it makes contact. So think about a tool like this making contact with this workpiece material. You're trying to produce a groove of depth of 20 microns. That contact might, depending on the hardness of the material, might eat up 5 microns. Okay, it's possible. That's one source of error. So in our system, we had a contact detection method, actually with an accelerometer that detects contact much more with greater sensitivity to minimize that initial, let's say, point of contact, to minimize overextension beyond the point of contact, right? That's also a function of the hardness of the material, obviously. So anyway, but that's one source of error. The other source of error in this case is that under dry conditions, the tool is also wearing. That's part of it. Forces are high. The tool may be deflecting as well, right? Some deflection may be there. But under wet conditions, you can see it got better. It's closer to 20, but still not at 20. With 12 watts, the dashed line is the target, nominal. 12 watts, yeah, depending in initial portion of the cut, this is length of cut, initial portion of the cut, it's actually pretty good, close to 20, right? Or at 20 almost. But then it starts to deviate. Why does it deviate? And the deviation increases at higher laser wattage. Why? What do you think? I'm sorry? Heated. And so what happens? Softens, yes, but the tool shouldn't move further in, right? Because I have a machine that controls my position. I'm sorry? It could stick because it's softer, but that doesn't explain the increase in depth. Think more simply. When you heat something up, what happens to it?
It is conducted through the lens. So when the tool is traveling through the lens, the more heat is transferred. So initially we expect something, but towards the end, since more heat is getting transferred in the process,
so there is some heat accumulation. I understand that. But I don't think that explains this phenomenon right from get-go at 18 watts. I'm at 25 microns. Yes, conduction, but somebody said the word, that expansion, thermal expansion. Okay, when you heat something up, it's going to expand. So what's happening to the workpiece? It's expanding. In addition to softening, it's expanding to initially expand. So, and you're producing, pretty high temperatures. 18 watts over 280 microns, the energy densities are pretty high. Right at the center of the laser spot, it probably is ablating some as well, but not ablating everywhere else because it's a Gaussian distribution, so it dies very steep. It's got a steep decline in energy, but bottom line is it's also expanding thermally. Okay, which means that it's going to expand further and the depth of cut will increase. Even if the tool is at the same position, it's going to increase. That's what's happening. So, but that's an easy problem for me to solve. I can compute how much energy I'm inputting. I can estimate the expansion, knowing the coefficient of thermal expansion, and I can compensate for it, which means that if I want to produce 20, I start with something less as my program depth of cut. There's a simple solution to it, right? So that's one solution. Anyway, but what you do see is that initially, depending on by optimizing the laser power, you can achieve the depth required. That's the point I'm making. Yes?
Thermal expansion, how does it increase the depth? The expansion is what dimension?
All dimensions, but usually in this particular case, you're only heating a very small region right in front of the tool. Okay? So that's the region that will exhibit the most expansion. Because temperature outside the region that is irradiated by the Gaussian beam is not going to be very high. You don't want it to be, obviously. So it won't be very high. So much of the thermal expansion is going to be at the point of irradiation and also closer to the tool. There is a distribution of heat, right? So you will see that thermal expansion. Okay. All right. So you can see here what the tool looks like. This is looking at the one edge of the tool. It's focusing in on an optical microscope. You can see under dry conditions, the tool has chipped. It's kind of the sharpness is gone, right? And this is under wet conditions. It's a little better, but it's also worn quite a bit. This is with laser assist. Not bad. It's still maintaining its sharp edge. There's some material sticking. There's some material sticking with higher laser power, softer material. It's going to adhere, etc. Right? So that is to be expected. Not ideal, but expected. This is showing you change in tool diameter because of wear. Okay, this is after machining for an extended period of time. This is showing for different cutting conditions. I didn't list all of them, but just let's look at this one. You can look at the paper if you'd like for more details, but this is showing you that 18 watt, 12 watts, both, all cases, the change in tool diameter. This is the nominal diameter that you started with, and then the final diameter after you've cut certain length. You can see that the change is less. It's not zero, it's less than without the laser assist, okay? Which is also important because the width of the groove will be affected by change in the diameter, right? This is showing you forces. Okay, there's a lot of data here, so let's not worry too much about all of them, but just look at this. This is showing you the first groove and the last groove. And I think in this case, there were 8 grooves or something that were cut. And for one cutting condition, there were 8 different cutting conditions. And you can see in general, with laser assist, the forces are less, right? Obviously, they're less for the first groove and they increase because of wear, but the wear rates are lower than it is without the laser assist. All right, so I've presented one idea of how do you enable micro-machining of hard metals and alloys, right? Using this thermal softening idea, very basic, simple idea. Let's talk about other hard materials, right? Such as ceramics. Ceramics are used for many applications, right? They are very hard, sintered ceramics. Unless you machine in the green state and then sinter it, that's one way. People have tried. But usually the way ceramics, there are many applications all the way from medical to non-medical applications to aerospace applications where you want to produce more complex shapes, features in sintered ceramic materials. So you want to use ceramics because of its high strength or elevated temperature resistance, inertness, right, to chemical environments and so forth. So there are reasons to use them, but then to shape them and produce these small-scale features or even large-scale features is a challenge, okay? How do they do that in practice? Generally, sintered ceramics are shaped by diamond grinding. They use a diamond-plated wheel and they will grind, which is, as you know, grinding is like a polishing process, like taking sandpaper. You take a sandpaper, how long does it take you to remove material? It takes a long time, a lot of effort, right? So same way, grinding is a bit better than hand, more consistent, but you're using a diamond-plated wheel and it's very expensive. And that's what they do, right? If you want to produce a groove or you want to produce something else in sintered ceramics. So how can I speed that process up? Because diamond tool is expensive. And if I consume more of that, that's going to add to the overall cost. There are reasons for me to try and optimize the process, right? Improve productivity of the operation and do it faster, without increase in or reducing the tool life, for example, right? So the approach we investigated, our idea was, again, simple idea, is you can soften. So you can use the softening approach as well, but you need much higher laser powers, right, to do that. And for certain materials like alumina, right, Al0203, their thermal stability is very, very, very good. It requires very high power lasers to be able to do that, which adds to your cost. Okay, so it's also not, again, in manufacturing, the whole basic goal of manufacturing is what? Doing things faster, better, cheaper, right? So I can do it faster, I can do it better in terms of quality, and I can do it cheaper. But some of these are competing objectives, right? Optimization criteria, they compete with each other. Certainly doing it faster, but doing it cheaper. They don't go hand in hand, unfortunately. But that's the goal. And so how can I do that in this particular case, which can be an advantage? So the proposed approach is, as I said earlier on, making use of this idea of thermal cracking. Make use of the properties of the material. In this case, it's not a metal. And I'm not trying to soften it because I need very high power lasers for that. But instead, I want to actually, I know that ceramics have they have some fracture strength. They will fracture. And they will fracture under tensile stresses. If you apply the right amount of tensile stresses exceeding the fracture strength of the material, you will fracture it. But I want to do controlled fracture. I don't want to fracture the whole thing. Then defeats the whole purpose. So I will irradiate with a laser, right? And generate very rapidly, because laser heating is very rapid heating and rapid cooling, right? When the laser moves away, you actually generate thermal stresses. Instantaneously generate very high thermal stresses, localized by controlling the process, the laser irradiation characteristics. You can actually generate sufficiently high, let's say, thermal radial stresses or circumferential stresses, depending on which mode of failure is easier to promote in the ceramic. You can actually produce cracks and weaken the material, as I described earlier on. That's the basic idea. So thermal cracking as opposed to softening, okay? And then I can still use a grinding tool, but now the grinding tool is simply removing already weakened material and cracked material. So it should require less forces, the wear on the diamond wheel should be less, and so on and so forth, right? That's my hypothesis, right? In a scientific method, we hypothesize based on our understanding. We present a hypothesis and we test the hypothesis. So that is our hypothesis. Can we do this? And indeed, is there a benefit, as I'm hypothesizing, in terms of lowering forces, etc.? So this is what we did. And so in this case, as I said, crack formation is due to tensile stresses generating during rapid cooling. It heats up and then it's cooled, and it's the tensile stresses generated during cooling, actually, after laser heating. So in order for me, I can do this experimentally and do trial and error to adjust the laser power, etc. But instead of doing that, smarter way as engineers and scientists is for us to think of what physics do we understand. We have some models. Can we use that to understand what knobs do I turn and how do I turn them in order for me to achieve this end result? We already know the physical concept, right? I want to generate sufficient tensile stresses to exceed the fracture strength of the material, which I know, okay? So I can use a thermomechanical model. You can do finite element modeling if you want, or there are analytical models that allow you to actually, knowing the energy distribution that you're using with the laser that's irradiating the surface, you can actually compute analytically the circumferential thermal stresses or the radial thermal stresses, the different components thermal stresses. Those solutions exist, right? So we did both in this case. The only advantage of the finite element model is that you can account for boundary conditions more properly if they're more complex, right? But if you're only irradiating a very small region, then you can treat the whole problem as, plane strain or plane stress or whatever, and plane strain, and you can use analytical solutions. Has some limitations, as we will see, but it serves the purpose though. And then once we have determined the size of the thermally cracked region for given laser parameters, or the other way around, the size because you're going to produce that feature. So given the size, what should my laser power be? What should my energy distribution be, such that I generate thermal stresses that exceed the fracture strength of the material? That is the objective. You can answer that question using the model, and then you do this laser scanning process, right? And then once you've done that, you try micro grinding. In this case, we did micro grinding. We are trying to produce micro scale features in the weakened region and see what happens, right? So this is the analytical model. It exists. In 1960, somebody worked this out. Bowley worked this out. that you can actually, there's some assumptions, obviously. Any analytical model, you make certain assumptions. The assumption here is it's a plane stress assumption, which says that this H over 2R, R is the radius of the region that is actually being affected, okay, by the thermal stresses. H is in this case the width of this region. So they were looking at a disk, essentially, right? So there's an assumption of plane stress, which we may be violating a bit, but as a first approximation, it's an easy model for me to use, right? So we did that. You can actually compute the radial stresses as a function of temperature, coefficient of thermal expansion, alpha, and you can do the same thing for circumferential stresses as well, right? So depending on tensile stresses, where they're generated, they could be generated in the hoop direction or circumferential direction, radial direction, or tensile. If sufficient, whichever one is sufficiently high, that is exceeds the fracture strength of this known fracture strength of the ceramic, then you'll generate cracks, right? That's the idea. So this shows you using that analytical model and using, in this case, a reaction-sintered silicon nitride, which is a ceramic, okay? It has a Vickers hardness of 1400, and it's being exposed to a laser or irradiated with a laser at 25 watts at a certain scanning speed and a spot size of 280 microns. Under those conditions, this is looking at the radial thermal stress distribution, right? And the fracture strength of this composite, of this ceramic is 350 MPa. So in this, I put 350 MPa, right? And this is the distribution predicted by that analytical model for the Gaussian temperature distribution, energy distribution that you're providing as input, right? And as a function of radius, distance away from the center of that circular region that is being irradiated. And you can see that it says that you will produce stresses, fracture stresses exceeding or at least equal to 350 megapascals up to 195 microns from the center. So a radius of 195 microns within that region, I should generate thermal stresses that exceed or are equal to the fracture strength, okay, of this material. So that tells me, okay, by changing my laser power, scanning speed, spot size, I can play with those to determine what size I want to generate these thermal stresses that exceed the fracture strength of the material using such a model. That's a much smarter way for us to do this, right? Rather than just trial and error, which you would have to do experimentally. It's expensive to do. You don't want to do that. So that's the advantage of this. Now, this is, okay, we are making some assumptions. How good is my plane stress assumption? May not be a perfect assumption in my case, given the geometry. I'm using a block, etc. It's not a disk, and so forth, right? So the boundary conditions could be different, or the assumptions being made in terms of plane stress may not be as good. We will see. So we want to test that hypothesis as well. So we use a finite element simulation where I can relax many of these assumptions, right? And apply the boundary conditions. So boundary conditions, I'm interested in some room temperature at every node, that you start out with some temperature, or start out with the temperature, in this case, whatever the temperature distribution is that is being imposed by the laser on top of it. And then you fix all the other nodes at the bottom. So you don't want rigid body motion. Otherwise you won't be able to solve, right, the problem. And you solve this, it gives you the temperature distribution, right? From the temperature distribution in a finite element model, you can also calculate the stress distribution, right? So this is showing you the radial thermal stress distribution for, in this case, scanning in this direction at some point for the same conditions, right? So I can do this, right, using a finite element model or the analytical model. This is showing you what happens if I actually do this in an experiment, right? So same conditions, and I have scanned the surface of this reaction bonded silicon nitride, and this is looking at the cross section, right? And you can see here that there is a depth of region that's affected, 30 microns, according to what I can see from this image. And there is a small region here where outside of the white region, small region here that actually is amorphized, okay? So essentially, it's like taking all these, what is a sintered ceramic? particles have been bonded together under heat with heat and pressure. So you just basically disaggregated these particles. So it becomes amorphous, like powder. Powder is amorphous, right? So that's really what has happened here. And you can see that indeed there is also some ablation. You can see there's already a groove that has formed of some sort, right? Some of it is because this amorphized powder can fall off, right? Because already weak, I don't even need to grind it, okay? But region below it is weakened, but it's not amorphized, okay? That's what has happened. So now I do this depth of heat affected region. I can predict it using this model, right? Because I have a model which tells me what the distribution of radial stresses and circumferential stresses in this volume are for given laser parameters and scanning conditions. So here is a comparison of using the analytical model, the experiments, and the finite element model. Depth of that affected region, I showed you a picture, 30 microns. In this case, changes when you're varying the laser power, right? So here the laser power is increasing for one speed. This is slow scanning speed. And the next one is same laser powers, same trend, but for a higher scanning speed, okay? And in general, at a higher scanning speed, you can see the depth is a little less, right? Now, any idea? Does this make sense to you that at a higher speed, it's less? The depth to which I am impacting the material and weakening it is less?
Less heat generation at higher scanning.
Why?
Higher speed changes the rate kind of.
There is no rake. There's no cutting here. There is absolutely no cutting. I'm just scanning. There is no cutting at this point, right? This is only scanning the surface with a laser. Interaction time is less. Exposure time is less, right? So therefore, obviously, mechanism by which heat is transmitted is through conduction, okay? When laser matter interact. And so indeed, so yes, you're right that it is less, and it's less because there's at higher speeds, lower temperatures are produced because of lower interaction time, okay? And so it's not surprising. I mean, this type of common sense check you should be doing. Hey, does this make sense? Does this result make sense based on my physical understanding of the process? Don't accept everything that you see. You have to basically question it, right? Am I getting it right? And so this is what it says. All right. Error in prediction is pretty good, 15%. That's actually in my books, pretty good. Okay? Pretty good if I can, even with the analytical model, I actually, analytical model you can see tends to over predict at higher laser powers. Okay, because I'm probably not modeling the boundary conditions, the assumption of plane stress starts getting a little iffy under those conditions at higher laser powers. You see that. But nevertheless, 15% is not bad at all. Okay, now this is showing you what the surface looks like for one condition at 18 watts. In this case, the desired depth. And here we are overlapping passes. So you have to design this. You have to design overlapping passes to ensure that the entire surface area is thermally cracked. The entire surface area where you're going to remove material is thermally cracked. Unless you have a laser with a large spot size and enough energy density to do it in one pass, which we didn't. So because of that, we need to scan, right? So this is what has been done. Yes?
So but when we have overlapping passes, reheating is possible.
Yes, indeed.
That would complicate the...
It could, but the thing is, you have already cracked regions, right? So at most, what would you do? You would probably burn off the binder some more because it's already amorphized, right? Or below the region that is amorphized, you would further crack it, maybe, right? So that's not a bad thing. So as long as it's within the depth to which I want material to be weakened, it's okay, right? So indeed, yes, you are affecting it. Now, that overlap, design of how much that overlap should be also needs to be optimized, okay? All right, so we did this. Now we grind. Now the cutting tool comes in, okay? After I weakened it, now I take a tool and it's like me taking a tool and scraping off, right? I mean, So intuitively, that's what I'm trying to do. So here is measuring the grinding force, right? And in this case, you can see it's for one condition. I gave you some data. You want more data that's in that paper. But laser power of 15 watts, spot size of 280 microns. And you can see here that without, and there's a number of grinding passes, okay? Because you can't remove all of this in one pass, okay? Because some region is amorphized, it's very weak, but you want to produce a 30 micron depth. Below that, it's weakened, cracked, but not completely amorphized to just fall off. It requires some force to remove. So there are some forces, but you can see here that in general, the average and maximum forces are shown here. So this is basically the average force, the solid lines, the dashed lines are the maximum values. And you can see that for the laser assist, it's much lower. Okay, so I've achieved I've tested, proven my hypothesis that this will benefit my ability, make it easier for me to remove the material, right? This is what the tool looks like. These tools are actually micro grinding tools, okay, that are on the order of whatever, 200, I forgot the size, it's listed there. And they are, you can see here, there are abrasives, diamond abrasives that are actually embedded in this tool or bonded to the surface of this tool. This is not the greatest quality tool. Back in that day, back when we were doing this, we found only one vendor. Now, the Germans actually make better quality tools. And today, you can buy much higher grade diamond micro grinding pencils. You can buy them today, actually. This is some, almost 15 years ago when we did this. So you can see here, without laser assist, it's almost balded. I mean, the abrasives have either come off, essentially been pulled out of the binder, or they've basically been worn down, right? So you can see the bald spot here at the bottom of the tool. This is the bottom of that ball nose micro grinding pencil, okay? I mean, it's nominally meant to be square, but there is some rounding, as you can see, because of limitations to be able to produce this. And then this is before grinding, after grinding. This is with laser assist. There is some balding. It's not zero, but it's less, okay, is what it shows. Can you improve this further? We were doing all of this dry. So you wouldn't do this dry. You will use some coolant or lubricant of some sort in practice. If you do that, you'll probably see much less wear, okay? At least over the length of cut that we used in these experiments, right? Or you can go much longer. This is the other advantage. All right, so I guess I am going much faster today, or we have fewer, so almost at the end of my slides, but it's fine. What we can do is to discuss and have Q&A. I decided not to throw in much more information, thinking that yesterday I never got around to even completing my slides. So maybe today, maybe you're already tired. So the fewer questions. But anyway, so I've given you an idea, or at least introduced you to two ideas, right? Two approaches to produce microscale features in difficult to machine materials, such as hardened steels or other types of hard metals and alloys, and using thermal softening as the principle, and then using controlled thermal cracking for brittle materials, right? Hard brittle materials like ceramics. I think by now, hopefully I've convinced you that machining forces can be reduced. But again, there needs to be a machining strategy. We talked about thermal expansion as being a challenge, so you have to somehow plan for that. You also have to plan for controlling the amount of thermal energy to minimize thermal damage in the material that's left after removal. And then tool life enhancement, which is the stuff I did not include here, which I could have, requires additional cooling strategies, which we have investigated. So keep in mind, for laser-assisted machining, you can't just flood with fluid, right? Applying a coolant or lubricant is not that easy because you're going to occlude the laser. You'll affect the ability of the laser to interact with the material to soften it, if that's the objective, right? So you be a bit more creative in how you actually enhance the life of the tool. So we've looked at other types of things, like, for example, using minimum quantity lubrication, but from the back, where the nozzle is behind the tool, because the laser is in front of the tool. So you point the nozzle at the back, and you control the misting. Minimum quantity lubrication, for those of you not familiar with it, is essentially, if you have seen machining operations being done in the workshop, for example, you probably have seen, the coolant or the fluid flowing liberally, right? It's called flood cooling. You're flooding the zone of cutting, right? Environmentally, there are challenges. That's why people for the last 20 plus years or longer, actually almost 3 decades, have been trying to reduce the amount of fluid used, because some of these coolants and fluids, we just don't know what's in them. Of course, there are standards, ISO standards, that specify toxicity of the fluid and so forth, but the ingredients are a mystery in many cases. Many of them are emulsions or oil-based things, but again, you have to be mindful. So it's best to minimize it. And then you have to dispose this, right? Disposal is also an environmental issue. So as a consequence, minimum quantity lubrication was pursued to reduce that flood cooling. How much fluid do I need? So idea is to use misting, essentially atomization, okay, of droplets that are actually, like generating a mist. You might have used a fan when you want to cool yourself, which has mist with it, right? It's the same idea, but using it to actually generate a mist. And the heat transfer conditions can be altered sufficiently for you to actually dissipate energy. Cool the tool. So what do I want to do? I want to cool the tool, keep the tool at a lower temperature always, because higher temperature means higher wear rate of the tool. So from the back, you mist it or cool it some way. Either you mist with the fluid, or you use a chilled air source, like a vortex cooling, like a Venturi effect, basically. You can make use of that, and you can actually direct chilled air at the back to kind of dissipate heat, extract heat, using convection really from the tool, because the tool is seeing some heat coming from the front because of the laser. So these things we have tried. That's what I mean when I say tool life enhancement requires additional cooling strategies, right? Chilled air, minimum quantity lubrication, etc. Rather than flooding, which you cannot do with the laser. Otherwise, the laser purpose of using the laser becomes, really goes away. So that's the limitation. So that is what I've shared with you, right? So I know we have about half an hour, a little more than half an hour left according to the time. So I will open it for discussion. We can have an open discussion. I'll do my best to answer questions. Go ahead, repeat the question, because then they cannot record it.
Fine, sir. So the process is about micro machining, right?
Yeah.
So will there be a definite need of a coolant or lubricant to enhance the tool life, or is there any other method being followed? Because this is micro machining. Like if it is a macro machining, then absolutely we have to go with a coolant or something.
Why? If I'll turn the question around and ask you, why for macro machining you think coolant is essential?
That is the major practice being followed everywhere.
Just practice doesn't make it right. What is the physical
absolutely.
reason?
Yeah,
what is the physical reason you think? Is there a good physical reason? Obviously, see, I don't think there is any difference between micro and macro from the standpoint of trying to cool it somehow or lubricate it somehow.
Our only aim is to maintain the thermal stability, right?
Correct.
So is there any other new method being followed, or?
I mentioned using chilled air, for example.
Will the effect be the same? Like
it won't be. That's why we study it, right?
Yes.
How well can it do it? Is it sufficient, right? And what we see, at least for laser-assisted processes, that it's easy to apply, right? I'm constrained. I can't use any method, because if I use any other method, traditional methods, then I will occlude the laser, right? And it will not soften the material or generate thermal cracks or whatever the case may be. So therefore, I'm limited to certain ways of doing it. So one is to direct chilled air. Depends on how chilled the air is, right? And you're relying on convection. That's one way. MQL is a combination of convection and droplet-based cooling, right? Evaporative cooling, effectively. So those are methods that, we have investigated. There are others, like people have tried cryogenics. Okay, think of cryogenics. But the problem, again, with cryogenic is the infrastructure required to implement, to deliver liquid nitrogen or supercritical carbon dioxide, CO2, okay, is not simple. So there are other considerations, in manufacturing. Economics of the process in the end will dictate not just the technology, not just the fact that you have a technical solution that works in the lab, but in practice, it has to work economically. Right? In other words, I should be able to, in the end, implement it at the least cost such that I can maximize profit if I'm a manufacturer with a commercial objective, or if it is, some other non-commercial activity, then I want to be able to still reduce cost, right? It's government-funded research or whatever, ISRO wants to do this. They don't want to just throw money at it. They want to minimize cost, right? So indeed, there are other practical considerations that might limit. So there are other ideas like cryogenics, cryogenic cooling. People have tried using liquid nitrogen, but the infrastructure, even at the macro scale, people have tried those things. They've all tried them. I am not aware of any other method that actually has not been tried. Every idea, to the best of my knowledge, has been tried. And there are applications where some of those methods work better than others. They all work to different extents, but they work better than others based on cost, time, availability, all of those types of considerations. So there isn't one answer, okay? And in micromilling, the same thing. Micromachining, same thing, right? Obviously, we are using much less in terms of amount of fluids or whatever, right, that we might be using. And in laser-assisted micromachining, I have additional constraints. So every available idea, physical idea that might be available in theory may not be applicable. So that's what you have to consider.
And talking about the coolants, like optimizing the coolant's composition, can it also reduce the amount of coolant being used?
Absolutely. But you need to be an organic or an inorganic chemist. The problem is that most of these coolants, industrial lubricants and coolants, are synthesized by chemists. And there are all kinds of additives, high pressure additives and other types of additives that are added. Oftentimes it's a mystery, it's a black box. They don't tell you the entire composition. That makes it difficult. So the only way for us as mechanical engineers to synthesize it, it's hard to do. We'll have to work with somebody. There are surfactants that are added. There are all kinds of things that are added, right? So yes, the short answer to your question is yes, but it requires somebody to actually engineer the liquid or synthesize the composition or do a study that actually, which they would have done, right? But they would have done not under machining conditions necessarily. Maybe they have tried some machining too, but oftentimes they're using tribometers and so forth to actually do basic simple tests because they're easier to do, to synthesize the chemistry of the fluid. But yes, but you need to collaborate with these chemists to be able to come up with the right composition, to give you effective cooling. Cooling is only one a function of what we call coolants, right? In fact, sometimes misnomer, we say lubricants, we're using a lubricant. The reality is in machining, lubrication probably is less effective. It's not as effective as a lubricant than it is as a coolant, right? Because for it to be effective as a lubricant, the fluid has to get in between the chip and the tool. And that region is highly stressed. And really, it is impossible to penetrate. The contact area is almost 100%, the real area of contact. So it's not that simple to actually lubricate that interface unless you artificially, that's why people do through-hole drilling, drilling with through holes. The coolants are actually delivered at the interface. You have to do things of that nature. They're there. Tools are available to do that. But that's, other than that, if you're just simply flooding it and expecting that it's lubricating, more than likely it's serving as a coolant, as a means to remove chips, remove debris. All that is a good thing, not a bad thing. Those are all other functions of the coolant/lubricant. And also carrying the heat away from the workpiece, which you minimizes thermal damage. Those are the functions that it typically is serving. Okay.
Thank you, sir.
You're welcome.
So, how laser assisted machining will affect the composite materials, sir?
Again, like I think I mentioned this yesterday, that you wouldn't use this process for, certainly not for polymer composite materials. You wouldn't use this. Okay. Polymer composites, it's not that you can't use lasers for composite materials or polymers even. You can, okay, you can use it to ablate, etc. But what is the motivation? What is the motivation for using laser assist? First of all, you have to be concerned about any damage you do, thermal damage you do to composite structure that might actually go, let's say, the skin of an airframe of an aircraft. There are very tight regulations in terms of, holes are produced, airplane structures, the holes have to be produced. They're all drilled mechanically. They're not done using lasers. It would take you much longer to do anyway with lasers, right? So I don't know what the practical motivation would be to try and use, or even a scientific motivation for using a laser. Now, metal matrix composites, different issue, right? Metal matrix composites are strong, very high strength. And so, yeah, there it might make sense to consider it, right? So it depends on the type of composite material that you're dealing with.
Okay, sir. So, what about the quality after manufacturing through laser assisted quality? By using laser, each affected zone will be greater, or?
Yeah, but as I mentioned to you, you can optimize it, right? You can control your laser power. You can control the distance D in front of the laser tool, etc., to affect, to ensure that the volume of material that is affected is only limited to the volume that's going to be removed by the tool. So once you've removed it, nothing else is affected below it. So that's a solvable problem, right? It's not if you blindly just simply use some laser power, excessive laser power, then you will deal with those challenges. But, you're an engineer, right? So, or you're training to be an engineer, you would use your basic knowledge of the physics to actually solve that problem. So it's solvable, as I showed you that, it's minimal, you can control it. There are even models to determine, right, what temperature distribution will be, etc., as a function of depth.
Okay, so comparing with the other welding methods and laser welding methods, the quality difference will be how, sir?
Well, yeah, so I was talking about laser assisted machining. I was not talking about laser welding or laser joining. That's a totally different process, right? Indeed, laser welding can produce better quality than conventional welding. Let's say using gas metal arc or some other welding process, right? Because you can control the energy source much better. So indeed, it's possible. People have shown that laser welding can generate better beads that you would use to join materials and so forth. But I'm not joining anything here, right? So I don't see the relevance of your question to what we discussed here. But yes, indeed, there is a difference. Yes, the short answer to your question is laser welding. But again, applicability. People have not given up doing regular welding, right? Using arc welding, for example, which are fusion welding process. It's a fusion welding process. So people are still doing that. People are even using basically arc welding for additive manufacturing. Wire arc metal additive manufacturing is a process, right? Where they're basically using welding knowledge to actually produce three-dimensional parts, very high deposition, energy deposition. Professor Samuel talked about directed energy deposition. Well, wire arc additive manufacturing uses a typical welding gun to actually deposit material at, kilograms per hour rates, as opposed to powder bed fusion or some other process, right? But there are pros and cons of both, right? A lot of energy, very rapidly you can add material, produce structure, but you can't control geometry as well, and so forth. But there are applications where that is more favorable. Okay, so yes, laser joining or laser welding processes will differ in terms of quality, in terms of compared to regular conventional arc welding processes.
Thanks.
You're welcome.
Sir, how the addition wear is reduced in this process?
Say that again, I'm sorry.
What are the methods to reduce the addition wear in this process? Addition.
Oh, adhesion.
Adhesion, yes, sir.
Adhesion. You mean built-up edge that
Yes,
I
sir,
was
yes,
talking
sir, yeah.
about. I see. Well, this is where application of minimum quantity lubrication, etc. What we have found is that using some lubrication technique or even using chilled air can actually reduce built-up edge formation. Okay, because there are two parts to it. One is how soft the material is, right? And the other part is how fast can you extract the heat when the material comes into contact with the tool. So extraction of heat is achieved through minimum quantity lubrication or some other direct air cooling. Direct air cooling or chilled air cooling will also affect the hardness of the material. If you extract heat from the workpiece material itself, there is you're trying to soften the material, but you'll soften it less, right? Which means it'll adhere less. So there is still optimization required. There isn't, and then that's not even considering the cutting conditions. In conventional machining, you know very well that if you want to minimize built-up edge occurs at low cutting speeds. Easiest way to address that is to increase the cutting speed, and it goes away usually, right? Those are also options, but there are limits to what you can do with micro tools, right? These tools, you can't go much faster as it is. You're dealing with, small tools that are fragile, and you're going to cut the material much faster. You're going to have higher forces, other effects that will actually cause the tool to fail. So there's limits to what you can do, but all of those are strategies to try and address, okay, the built-up edge issue.
Sir, actually, I just have a doubt in this laser-assisted micro machining.
Mm-hmm.
For metal salon, can you just repeat once again, like what's the process with the laser and the tool?
Let's see, is there, you can see it. So the basic idea is quite simple. This is the basic idea. Idea is you have a laser. This is thermal cracking. This one for metals. So the basic idea is you have a laser that is actually irradiating the volume of material in front of the tool. Okay, the tool is moving in whatever direction it's moving, but there's a laser pointed, actually laser spot that actually is directly in front, some distance away. That distance d is a variable, that process variable that you have to adjust and optimize. The region that is irradiated, shown by the red circle, is the region that is affected by the laser interacting with the material, and heat is generated, right? When laser matter interaction occurs, which I'm sure Professor Samuel talked about. So that heat softens the material. So it's softening the material directly in front of the tool, right? So by the time tool comes, the material that the tool sees is softer than it was before the laser irradiated it. That's the basic idea. And what happens to material when you heat it? It softens. A very simple concept.
Sir, actually, like, why can't the laser be tailored to the dimension of that milling area? Like, it's
Indeed.
basically a rectangle, right?
Indeed,
It
is
can
being-
be tailored to a rectangle to minimize the area.
you need that's called laser beam shaping.
Yeah.
Okay,
That-
it's not simple. You need much more sophisticated optics to do that. Why do I need to do it? I mean, you can. Just because you can doesn't mean you do it, right? It has to be economical to do it. So it's a way. If you have lots of money and time, then you could do that, right? But it's not necessary. If we can actually make use of a Gaussian beam laser or some other beam, standard lasers, right? There are hat-shaped lasers that have energy distribution like a hat, right? A bit more uniform than a Gaussian beam. But you can use any of these to control. Now, a Gaussian beam is not exactly, it's irradiating, and the energy distribution is like a Gaussian distribution. But by designing it such, again, even though it might extend slightly beyond the volume that is going to be removed by the tool, as long as the temperature rise is negligible, right? It won't matter. So yeah, you can do what you're saying, but it'll take more effort to do that. It's going to be a bit more complicated, your system.
Okay. Sir, and in what practical conditions do we apply this localized softening?
When you are trying to machine micro scale features using
Sir,
difficult to machine materials.
like you concentrate only on a single point, right?
It's not a point. It's
place.
still an area. right? Yeah.
Like a small area, right? But
Correct.
the milling is done to a large extent.
That's why you do scanning.
Okay. Fine.
You're doing this, the softening is occurring wherever the tool is going, but ahead of it, right?
Okay. Yes,
So, yes. Can you pass the microphone?
Sir, in case of ceramic machining, one phenomena is there, like brittle to ductile transition.
Mhm.
We need to maintain such a speed to get the machine. So with the help of this laser heating, still this phenomena exists, or we can machine it as if a metal or alloy?
So the way people have done ductile mode machining in ceramics is by taking advantage of ductile to brittle to ductile transition, right? That you're talking about.
Yes.
That occurs under certain conditions of stress that you can generate in the material. Generally at very low feeds, for example,
Yes.
you will generate brittle to ductile transition. We are not even making use of that here at all. That's what you would do in diamond grinding. Diamond grinding, you're grinding under conditions where you're removing very, very small amounts of material, where more than likely, because you don't want chipping, you don't want brittle fracture, right? You can't control fracture because then the geometry will be whatever. So you're actually, diamond grinding is occurring under conditions where brittle to ductile transition is the mechanism that is being taken advantage of, right? Here, we are not doing that at all. Here, we are saying, I want to weaken the bulk of the material, but that's a very slow process because the very low feeds are what you need to do that.
Yes.
And very low feeds means it will take you a very long time
Yes.
to produce a relatively large feature. Still micro scale, but relatively deeper feature. It'll take much longer for you to do. So here we are not even bothered with. Now you can, after you have done this, right, to get a better surface finish, let's say you need to produce a slot in this ceramic that's, let's say, 30
My
microns.
next question is what was the effect on surface finish between these lasers?
That's right. That's what I'm trying to tell you, is that if you need to produce a slot of 30 microns, then you could remove, let's say, 28 microns using this method or 25 microns using this method. And the last 5 microns, you can do diamond grinding to improve the surface finish, right? That's still faster than simply using diamond grinding. It'll take you much longer. It'll be a more expensive process. That's how you would get around the surface finish issue if you need much finer finish. Yeah. Okay. Yes.
So, when in laser scanning, what advantage does overlapping passes give to the process?
Nothing other than the fact that you want to weaken a larger area of material, surface area of material, or volume of material, I should say, than the size of the laser spot can do in one shot. So if I have a way of, let's say I have a much bigger laser spot size with sufficient energy density to irradiate this bigger area in one pass, then I don't need to do any overlapping passes. But I need a larger laser with sufficient energy density to do that, which is more expensive.
Yes, sir. So then basically overlapping means the same region is being reheated without affecting
Part of
process.
it, part of it. It's
Okay.
amount of overlap is what you control, right? If you only overlap 100%, you will only do that region, right? If I want to do this portion, then I'm going to overlap. How much overlap is what is a design parameter. You have to determine how much overlap. Ideally, zero overlap would be great. That would be the most efficient way, right? But it may not be enough because depending on the energy distribution, like I said, there is a Gaussian distribution, it decays very rapidly. So you may not produce sufficient cracking, let's say, right? Or softening. You're not doing laser scanning for the first method for metals. You're doing it simultaneously. Whereas the second method for ceramics, that's where we are doing laser scanning. That's where you need to optimize the amount of overlap such that you weaken the entire surface volume, right? That eventually you need to remove, which you can't remove in one pass. You know, if you had one laser that big and one tool that equally big, then you could just do, you know, one laser scan and that's it, and then do removal. But then that's expensive to build such a system, right? It's not as flexible. I'll only be able to do big things with it. Yeah.
Another question, sir.
Yeah.
In thermal cracking of the ceramics, you particularly mentioned a term confined thermal cracking or controlled thermal cracking. What does the term controlled thermal cracking mean?
Means that I am basically controlling the region of the material that is being cracked. So in other words, I'm confining the volume of material where thermal cracking is taking place.
So basically it depends on the tool, that micro tool.
No,
Okay.
it depends on what conditions you irradiate the surface with the laser. The tool could be something, but if I choose the wrong parameters for my laser, I will actually either crack a very small volume, which is maybe much smaller than the diameter volume swept by the tool, or much larger volume, which I don't want to do. So it has less to do with the tool. I mean, yes, the tool dictates the volume that I want to thermally crack. Okay? Because that's the only amount of material I can remove. That's it, right? Is that clear?
Yes.
Okay. Yes.
Sir, my question is related to metal. Means when we use machining with the help of laser.
Mm-hmm.
So while analyzing cutting force and power, whatever it is, so merchant circle diagram will be same as the means without the help of laser heating, or will be there any change in merchant circle diagram?
Merchant circle diagram, if you were to use a simple orthogonal cutting type of a model to analyze that, and I mean, outside of the limitations of that modeling approach, it has its own limitations, as you know. It's assumes plane strain, right? Plane strain conditions. Micro milling is not a plane strain process necessarily, but let's say you approximate it that way. The analysis technique doesn't change, but what changes is the properties of the material. In a merchant circle diagram, or merchant's analysis, I should say, merchant circles diagram is simply a force diagram.
Yes, sir.
That's all it is, right? What does the force depend on? You have to use merchant's approach, shear plane analysis. Okay, if shearing is the method, but for ceramics, shearing is not the method.
No, sir. In case of
Metals, yes, metals shearing would be the method. But then what would change? You know, there you're saying that the shear force is proportional to the shear strength of the material, right? So what changes with laser? The shear strength of the material changes. So you can incorporate that. Indeed, we have used that type of a model to build a model, okay, but then you have to account for other effects too. The strength of the material is affected by the strain rate as well, because you're deforming the material much higher, faster rates here, actually. The tool, the micro milling tool is spinning high speed, quite fast, right? So yeah, you can use that type of approach, but it's the material property that is being changed that you have to account for,
Sure.
because you're thermally softening it.
Thank you, sir.
Yeah, sure.
What about the dimension accuracy of highest aspect ratio holes?
Yeah, so
If the target depth is more than 200
yeah, so I
microns.
think there are limits to what you can do with this approach, right? With laser, because
As you said, 30
in
microns.
one shot it's difficult to do, right? Because if it's high aspect ratio hole, you would have to do it in stages.
Yes.
You'd have to do something like percussion drilling or something, in steps, basically. And therefore, you're going to be limited to some degree, right, to the aspect ratio, in my opinion. If you're doing a hole, it's a drilling process. So you can't really use this configuration at all.
Yes, this is a milling.
It's milling only, yeah. It'll not work for drilling, right? Because then how do you soften the material is the question. You have to have the laser pointing ahead of it, and beyond a certain depth, the laser will be occluded by the surface of the surface surrounding the hole.
Yes.
You won't be able to, irradiate the bottom of the hole.
Yes.
So there's limited. You really can't do that with this process.
Taper formation also the issue.
Yes, that too. But even assuming that you're going to do this in multiple steps, there's only up to a certain depth you can do this, beyond which the laser will not, the bottom of the hole will not see the laser.
Yes.
So that's a limitation.
Okay. Thank you, sir.
Sir, about the heating of the tool, sir, we are always trying to cool the heated tool now, sir.
That's true.
Is there a way we can, insulate the tool or something, like a coating or something?
Indeed.
Is it practical?
It is practical, and we have investigated. I didn't go into it, but we have some papers actually looking at coating the tool using, insulating materials, if you will, right?
Yeah.
Using ceramic coatings. Okay.
So is that possible to do it in micro milling?
Yes, we have tried it. Indeed, there's a paper where we actually tried that. We used, they're not entirely ceramic coatings. They're like TiAlSin type of coatings, or titanium is still there. There's metal. You need some binding material. And yes, you do improve tool life. But you're right that this is counterintuitive, right? You ideally want to remove heat. You want to minimize how much heat the tool sees. But here we are adding, right? But we are adding to soften the material. But some heat does get conducted to the tool too, right? So, which is why you need either cooling methods or MQL from the back. Remember I said, chilled air from the back, or minimum quantity lubrication from the back. Misting from the back of the tool.
If the tool is, not getting conducted, so the heat will be in the workpiece, and then the material will be getting removed.
Right.
And the tool will be still cool, like it won't.
Well, you're trying to keep it cool by extracting heat quicker.
Not extracting, sir, without allowing the heat to enter the tool.
Yeah, but how would you do that is the question.
That's what I asked about insulating the tool.
Yes, but how would you insulate the tool?
By kind
thermally
of coating.
insulate it. How would you thermally insulate the tool without affecting its cutting properties?
That's the question I'm about.
That's why I said to you that there's limits to what you can do. Unless you can come up with a pure ceramic coating that can last and can adhere to the tool, then you can do that, right? So we tried that, and yes, it helps. But again, you need to work with coatings developers to be able to develop insulating coatings like that. Unfortunately, most of the coatings have metals in them too, in order for you to have proper adhesion and different properties. So, like common coating material in cutting tools is TiAlN, right? Titanium aluminum nitride. Aluminum nitride, yes, I understand it's ceramic, but there's titanium still, right, in it. And so that is a limitation. So unless you can come up with extremely thin, maybe you come up with some other, that is a coating problem. Somebody has to develop some CVD coating technique where you can coat with sufficient adhesion to the tungsten carbide substrate, a thin layer or sufficiently thin layer of ceramic coating, then yes, in principle, yes. But do I know what coating is available to do that and how to do it? No, I don't. Yeah.
Thank you.
Sir, actually we are using laser to soften the metal, right?
Correct.
It induces thermal expansion.
Yes.
So does it create some kind of residual stresses?
Oh, it's possible. But again, thermal.
Because like the other part of the metal is cooled, right? It's
Correct.
a normal temperature.
Correct.
So when this alone expands,
Yes.
Actually they resist the expansion, which
Correct.
are not heated.
Correct.
So they cause a compressive stress while they expand due to the tensile stress. So
But
does it do any residual stresses?
No. So you certainly can have some. You will have some residual stresses, right? We haven't done residual stress measurements. Others have done it. Keep in mind that yes, what you say, there's expansion, but I'm talking about thermal expansion, almost like elastic, growth that can be recovered the moment you remove the heat. Obviously, I'm trying to soften the material. And yes, the neighboring material is going to resist it because it's not heated, right? But I'm removing the material. I'm removing the softened material. So there will be some residual stresses. There are people who have actually tried to analyze or measure residual stresses. But is it worse than it is if you were to not use a laser? That I do not know the answer to that question. In principle, if you think about what happens when you add heat, generally it's bad because you generally tend to produce tensile residual stresses with more thermal energy being input to the material. But here we are confining that thermal energy only to the volume that's being removed, right? So my hypothesis, I have not tested it, is that there will be some residual stresses because you're deforming this material inhomogeneously anyway. But it shouldn't be any worse than it is if you were to not use the laser. Unless I think you don't control the laser energy, and confine it to the volume that you're going to remove. In which case, I suspect, you'll do other things that won't be good. Yeah. We haven't really spent time. I mean, think about it. These are very, very small scale features. If you use X-ray diffraction to do laser, residual stress measurement, and the spot size of the laser, spot size of the X-ray, and the depth of penetration of the X-ray, I'm producing a feature that's 30 microns. And the depth of penetration of the X-ray, unless I do something like glancing angle X-ray, which may be hard to do in this bottom of the slot, will be on the order of the depth of the slot, which means I'll get one data point averaged for that entire thing. So we didn't see the point of doing it. Our first question was, can I even produce these features? And is there even any benefit? If I can't produce the geometry, I can't produce it efficiently, then I don't even need to worry about residual stress, right? Because it's not practical. Now that I can produce it, then yes, that's a question to ask. Okay, what happens to residual stress, right? So we stopped. We didn't go beyond. There are others who've done work in this space, actually, that you can look up doing residual stress measurements.
Okay.
Yeah.
So in this work, you have not considered surface roughness. Was that not part of objective or?
It wasn't the primary objective initially.
Okay.
I didn't show you any results, but
Yes,
if you look
yes.
at some of the papers that are cited, there is some surface roughness data as well. So yes, there is increased roughening.
Increased roughness.
Yeah. But again, this is where the strategy comes into play. Because if your material, at least for metals, not for ceramics, but for metals, you are, just like we talked about for ceramics, we said, okay, well, I can remove most of the material easily using this thermal cracking. And then the final pass of 2 or 3 passes, I can do diamond grinding type of method, which will speed up the whole process, right? So in an analogous fashion, you can do something similar in metals too, where the last final pass, you don't use a laser. then you don't produce that. You don't have this increased roughening because of softer material.
Sir, and one more question, like on slide number 16.
Yeah.
Like in some medium power, like burr formation is more. Why is like that?
Say that again. Medium power.
Yes, sir.
Burr formation is more than what? It's actually it's less than for the 18 watts. 18 watts is a higher power than 12 watts.
So actually, what is causing the more burr formation?
You're softening the material. So when the material is softer, it flows more easily, and material gets pushed out to the sides. Right? You can't have zero burrs. Right? I mean, it'd be great if you have zero burrs. Even in laser micromachining, with no mechanical tool, you have burrs. If you laser drill a hole, just purely through laser percussion drilling or regular laser drilling, you will actually have at the rim of the hole, if you look at the cross-sectional view, you'll see ridges. Okay, it's not avoidable. But the reason that is happening is because you're softening the material, and material flows more easily, right, to the side. It's being pushed to the side. And usually it's analogous to what happens in drilling. In just conventional drilling, you produce an entry burr and an exit burr, right, when it exits. So think about milling. The tool is entering, there's a burr on the left-hand side as it's rotating. Exiting, it's producing some burr, because the chip thickness is very, very small at those. So material cannot be sheared easily. It's being pushed. That's why it's happening. And the material is softer, you're pushing more. It flows more easily when you push on it. That's the reason why.
Okay.
Okay? All right.
Sir,
maybe last question. It's 12:30.
I have one
but
question,
yeah.
sir. Actually, if I increasing that length of that machining, it may affect the force on that cutting tool.
I didn't understand your question.
Sir, if I increase that cutting length,
Yes.
suppose you are doing that 18 mm like that.
Yes.
So when I increasing that cutting length, it
Yeah.
may varies that cutting force also.
Sure, the more you cut, the tool will wear, and with wear, the forces will increase.
So how can you maintain that constant cutting force?
You cannot. I mean, in the sense that you will have to limit the length of cut to ensure that you don't, the wear-induced forces don't go beyond a certain point, which is harmful for your surface finish or accuracy or whatever you're trying to control.
So can I control
No,
the
even in
cutting-
conventional machining, forget about this. In even conventional machining, you can't really ensure zero wear, right? Till the tool is fresh, you can approximately control the force. That's it.
After that it will affect that.
Yeah, but that
build-up
is true in any
resistance.
machining, right? It's not specific to laser-assisted machining. In fact, the laser-assisted machining, in theory, I should be able to cut longer before that same amount of wear is produced. Because I'm cutting, forces required and the energy dissipated is less. Because the material is weaker, softer, right?
Thank you.
Yeah, you're welcome.
Done with the questions.
All right, very good. Thank you very much. Enjoy the rest of your day.